Picture this. You're working on a brand new embedded software project. You've selected a really capable little chip, an STM32 S051 microcontroller.
Which is a solid choice, for a lot of applications.
Exactly. It has plenty of processing power for your needs, but you're dealing with a hard ceiling of exactly 64 kilobytes of flash memory.
Right. And in the embedded world, that is a hard limit.
Yeah. So because you want your code to be clean, readable, and, maintainable by actual human beings, you naturally want to use the standard hardware labels provided by the manufacturer.
Makes sense. Nobody wants to read raw hex code.
Right. But the second you add those standard readable names into your project, you lose 45% of your total storage space.
Wow.
Yeah, you forfeited nearly half your memory before you've even written like a single line of your actual application logic. Welcome to today's deep dive, by the way. Our mission today is exploring a really fascinating technical document called the FURS Notebook ulm-podcast.txt.
It's such a great read because it addresses this brutal reality for developers in this space.
Yeah, because when you're writing code for highly constrained hardware, every single byte is prime real estate.
Absolutely. And the specific problem you're describing here revolves around using a language called Microprocessors Forth.
Right, which is quite popular, right?
Oh, yeah. Forth is incredibly powerful for embedded systems because it's interactive, it's lightweight, but it has a really unique architectural quirk.
Okay, let's unpack this. We need to understand the stakes here.
Right. So Forth stores every single word you define in a dictionary, and that dictionary lives directly on the flash memory of your target microcontroller.
So just to clarify for the listener, in a normal C programming environment, the C compiler lives on your powerful laptop, right?
Exactly. Your laptop does all the heavy lifting.
But with Microprocessors, the interpreter and the dictionary of commands live physically on the tiny STM32 chip itself.
Yeah, that is the core of the issue right there.
Yeah.
Now, bring in the desire for human readability. Any developer working with ARM Cortex chips wants to use CMSIS names.
CMS?
Yeah, CMSIS stands for Cortex Microcontroller Software Interface Standard. It's a universal naming convention created by ARM and chip vendors, so developers don't have to memorize raw, meaningless memory addresses.
Oh, thank goodness.
Right. So instead of writing raw hexadecimal, you get to write a nice, clear name like GPIO CBSR RBS9.
Which, tells any engineer reading the code that you're targeting the bit set reset register on GPIO port C, specifically bit 9. It's self-documenting.
Exactly. It's beautiful.
Yeah.
But bringing those beautiful CMSIS names into Microprocessors Forth is where the nightmare actually begins.
Because of the dictionary.
Yes. There are roughly 3,700 distinct register and bit field names for this specific chip.
Wait, really? 3,700?
Yeah. And compiling all 3,700 names into that on-chip dictionary is what eats up those 29 kilobytes.
That's insane. To put that in perspective for you listening, paying a 29 kilobyte tax on a 64 kilobyte chip just for the privilege of readable variable names is fundamentally unacceptable in embedded engineering.
You literally cannot ship a commercial product if half your storage is devoured by the names of the hardware pins.
It's like buying a beautifully efficient 64 square foot tiny home, but then realizing your perfectly labeled storage boxes take up 29 square feet before you've even packed a single shirt. You're paying a massive premium just to have nice labels.
That's a great analogy. It's a massive memory tax.
Which leads us to the tool we are exploring today, outlined in the source, FURS, or the Forth Upload Replacement System. This system proposes a massive paradigm shift in how we handle this memory tax, doesn't it?
It really does. FURS completely flips the script on how human-readable abstractions are managed. The core philosophy here is dead simple, yet incredibly powerful.
Lay it on us.
You keep the CMSIS dictionary entirely on your host machine, meaning your development laptop or desktop, and you do not put it on the target microcontroller at all. You separate the human environment from the machine environment.
Wait, I need to push back on the mechanics of that.
Go ahead.
If I'm writing my code on my laptop using the human readable string GPIO CBSR RBS9 and I upload that to the microcontroller, the chip's dictionary does not contain that word. The chip literally has no idea what that string of text means. Doesn't the execution just immediately crash?
Well, yeah. It absolutely would crash if you were sending that raw text to the chip. But FURS does not send the raw text.
Oh, good.
It inserts a build pipeline between your laptop and the microcontroller. Think about how a standard C compiler behaves. When you write C code, you use symbolic names, right?
Right.
But the compiler resolves those names into raw, absolute memory addresses before the binary ever runs. The physical chip only ever executes the addresses.
Ah, I see where this is going.
Yeah, FURS applies that exact same compilation philosophy to Forth. It intercepts your code at upload time, looks for those readable CMSIS words, and dynamically resolves them into absolute addresses and bit manipulations.
So by the time the code is flashed over the wire to your chip, it contains nothing but pure, unadulterated hardware addresses.
Exactly. You get to keep your pristine, self-documenting code on your monitor. But the chip only receives the mathematically precise instructions it needs. You save the entire 29 kilobytes.
That makes perfect sense in theory. But understanding the philosophy is one thing. I want to know if this holds up mechanically. How does a string of characters turn into a hardware instruction without breaking the interactive nature of Forth?
Well, the source details a four-stage transformation pipeline to achieve exactly this.
Let's walk through it.
What's fascinating here is that the pipeline is a masterclass in utilizing incredibly fast standard Unix text processing tools. The heavy lifting is done by a utility called GMA.
GMA, that's a macroprocessor, right?
Right, it's designed for advanced pattern matching. So let's look at stage 1, which specifically targets bit fields. You run your human-readable source file through GMA, feeding it an auto-generated pattern file called bitfields.pat.
And what's in that file?
It contains over 7,000 highly specific substitution rules.
Oh, wow. That's one rule for every single configurable bit on every single peripheral across the entire microcontroller.
Correct. So when GMA scans your source code and encounters a word like GPIO CBSR RBS9, it triggers the corresponding substitution rule. It instantly replaces your human-readable name with a densely packed string of Forth code.
What does that code actually look like?
It looks something like this: 48,819, then 1, then 9, then 1, and finally BSS.
Okay, let's translate that output for the listener because it definitely looks like gibberish at first glance, but it's actually a set of hyper-precise mathematical coordinates.
Yeah, break it down.
The first part, the 48,818, is the raw hexadecimal base address of the register. The 9 is the bit offset, meaning we are walking exactly 9 steps down the register to find our target bit. Right.
The
The 1 dictates the bit width, meaning we are only flipping a single bit, not a whole block of them. And finally, BSS is an atomic bit field set operation provided by the FURS library.
Yeah, and that BSS operation is absolutely crucial. It takes those coordinates and safely writes to that specific bit without accidentally altering any of the neighboring bits in that register.
So it handles the low-level read, modify, write cycle seamlessly.
Exactly.
Okay, that's brilliant for flipping a single bit, like toggling an LED or enabling a specific interrupt. But let me challenge the scope of this. What if I don't need bit field granularity?
What do you mean?
Well, often you need to read an entire register at once. If I'm trying to pull a current count from a hardware timer, I don't want to read it one bit at a time.
Oh, sure. The pipeline architects anticipated that requirement, which brings us to stages 2 and 3.
Okay, how do those work?
If you write TIM2CNT to read the entire 32-bit counter of timer 2, stage 2 steps in using a different pattern file named registers.pat. It swaps that overarching register name directly for its absolute memory address, which would be 400 and 224.
Got it. And stage 3?
Stage 3 processes symbolic constants using constants.pat. So if you're configuring a GPIO pin and you use a readable constant like analog or push-pull, stage 3 replaces those text strings with their literal binary values.
Like turning them into pretend or Persero 1-1?
Exactly.
So by the end of stage 3, every single human-readable hardware reference, whether it's a single bit, a full register, or a configuration constant, has been meticulously translated into raw hex addresses and binary math.
You've got it. And then the pipeline runs stage 4, the final optimization. It applies a pattern called strip.pat.
Which sounds like it cleans things up.
It acts like a minifier. It aggressively strips out all the remaining white space, all your helpful developer comments, and all the stack effect notations. It compresses everything down into a minimal, incredibly dense Forth binary file called upload.fs.
Oh, wow.
Yeah, and that hyper-compressed file is the only thing that actually gets transmitted to the McCrisp Stellaris interpreter on the chip.
It's basically the embedded equivalent of minifying JavaScript before deploying it to a web server. But this brings up a massive logistical hurdle.
What's that?
We just casually mentioned that this pipeline relies on over 7,000 substitution rules.
Yeah.
I mean, managing a text file with 7,000 regex patterns manually would be an absolute maintenance nightmare. One typo, and you're writing to the wrong memory address, which could brick your hardware. Where do these .pat files actually come from?
Oh, they aren't written by hand. They are
Yeah.
completely auto-generated from the single source of truth provided by the hardware manufacturer.
Oh, thank God.
Yeah. STMicroelectronics publishes an official XML document called the CMSIS-SVD file. SVD stands for System View Description.
And what's inside that?
It's a monolithic, highly structured document that exhaustively describes the entire architecture of the microcontroller, every peripheral, every register, every single bit field, and what they all do.
So FURS isn't maintaining these rules manually. It's ingesting this massive XML file and digesting it into Unix patterns.
Exactly. It processes the SVD file using a series of XSLT transforms. XSLT is a functional programming language specifically designed for transforming XML documents into other formats.
Right. So how does it transform it?
First, the system runs a quick GMA pattern to sanitize the XML, fixing weird whitespace issues and translating C-style hexadecimal numbers into the Forth-style $ notation. Then it applies a heavy-duty XSLT style sheet called unfolded.xsl.
Now, the source mentions this unfolding process is necessary because SVD files are heavily compressed using derived from attributes.
Yeah, think about it from the manufacturer's perspective. If a chip has 3 hardware timers that function identically, the XML does not write out the full configuration 3 times. It describes timer 1 in full, and then for timers 2 and 3, it simply says derived from timer 1.
Ah, that makes sense for saving space in the XML.
Right. But the unfolded.xsl script recursively resolves all of those links. It expands the XML tree so that every single peripheral is completely self-contained in the data structure, with no external dependencies.
Here's where it gets really interesting, because SVD files have a hidden trap. They don't actually give you the absolute final memory address of a register.
No, they don't.
They give you a base address for the overall peripheral, and then an offset value for the specific register inside it. If you want the actual hardware address, you have to do the math yourself.
That's a critical detail, and doing hexadecimal math inside an XML transformation is notoriously difficult.
Really? Why is that?
Well, XSLT is a functional language. It does not have simple imperative loops. So, FURS utilizes a script called process-hex-tunum, which employs a recursive template.
Okay, so it steps through the math recursively.
Exactly. It steps through the string of hexadecimal characters one by one, recursively multiplying and adding to convert the base address and the offset into decimal, adds them together, and then converts them back into a concrete absolute hardware address.
Wow.
Yeah, it essentially pre-computes the entire memory geography of the chip during the build process.
It's front-loading all the computational heavy lifting onto your laptop so the microcontroller doesn't have to think about it at all. And once it has this fully resolved, mathematically perfect XML file, the workflow branches, right?
Right. One stream outputs those GMA pattern files with the 7,000 rules. But the other stream builds something I think is a game changer for the developer. It builds full Swdcom databases.
Generating a relational database from the hardware specification, that is an incredibly powerful byproduct of this pipeline.
It really is. Think about what this means for you as a developer sitting at your keyboard.
Yeah, normally if you forget the exact name or location of a register, you have to stop what you're doing, open a 1,000-page PDF datasheet, and search through chapters of technical tables.
Exactly. It completely breaks your flow.
But FURS provides a command line tool called furs relational. Because the entire chip architecture is now indexed in SQLite, you can instantly query your chip's memory map right from your terminal.
Yeah. You can search for any register containing the letters CNT or dump the entire layout of the real-time clock peripheral in milliseconds.
You're completely replacing the friction of manual PDF searching with standard, lightning-fast database queries. It gives you unprecedented programmatic visibility into the hardware you're trying to control.
It's huge for productivity.
That visibility is amazing. But I do have to bring up a concern that I know is flashing in the minds of our more seasoned technical listeners right now.
Okay, let's hear it.
We are talking about multi-stage macro processors, recursive XSLT, XML transformations doing hex math, and parallel generation of relational databases. This sounds dangerously close to the bloated complexity of a modern web stack.
I can see why you'd say that.
Is using FURS going to require managing massive Docker containers, or navigating a tangled dependency hell of Python environments and node modules?
It's a very valid concern. In modern software, we often solve problems by stacking massive dependencies on top of each other. But the answer here is a definitive no.
Really? No heavy dependencies?
Nope. The brilliance of the FURS architecture is its uncompromising adherence to Unix simplicity. It relies entirely on rock-solid, decades-old utilities. GMA is a single-file, portable C program that you can compile instantly on any machine.
Okay, that's refreshing.
And the XSLT processing is handled by XLT-PROC, which leverages the standard libSLT library that is already baked into almost every Unix-like operating system in the world. And Squall, famously, requires zero configuration or server management. It just reads and writes a local file.
So there's no massive tool chain to install at all? If you have a terminal, a standard C compiler, and make, you're ready to go.
Exactly. The entire symphony of these transformations is coordinated by a single make file. You type make all to ingest the SVD file and regenerate your databases and patterns. And when you're ready to test your code, you simply type make upload.
Let's talk about that upload process for a second. One of the main reasons people use Forth in embedded systems is because it is interactive. You can type commands live and see the hardware react. Does putting a compiler pipeline in the middle ruin that interactive REPL experience?
Actually, no. FURS preserves the interactive experience beautifully by using a background debug daemon called SWD2.
And what does that do?
It's a FreeBSD binary that connects directly to your microcontroller via a hardware debug probe. When you type make upload, the make file fires a Unix SIGQRDT signal to that daemon.
Oh, clever.
Yeah, the daemon immediately catches the signal, scoops up your densely compressed upload.fs file, and flashes it straight into the chip's memory.
And while that daemon is running in the background, you interface with it using a Python readline wrapper called swd2rl.py, right?
Exactly. This gives you a fully featured terminal with tab completion for your Forth words, persistent command history, and live hardware access.
And here is the true magic of the system. Because the CMSIS resolution pipeline is running live on your host machine's REPL, you can type a human-readable command like TIM2CNT at dti into your terminal. You're basically asking to read the value of timer 2.
You hit enter, and the terminal instantly prints the timer's current value.
Even though the word TIM2CNT literally does not exist in the dictionary on the microcontroller, the host REPL intercepts your keystrokes, cross-references the Squally database, translates the readable name into the raw hexadecimal absolute address, and sends only the raw memory fetch command down the wire to the chip.
And the chip just responds with a number, and the REPL displays it to you seamlessly. You get the ergonomic comfort of a high-level language, but the execution profile of bare metal assembly.
It bridges the gap between human abstraction and machine execution perfectly. Okay, we've covered the theory, the mathematics of the XSLT, and the Unix pipeline. But I want to see if this actually survives contact with reality.
Sure. Let's look at a real-world example.
Can you build a fully functional, hardware-reliant application using this without the memory footprint exploding? The source document includes a real-world demo reading an LMT01 temperature sensor. And looking at the specs for the sensor, it's not just a simple analog voltage read, is it?
Not at all. The LMT01 is a very unique 2-pin digital sensor. When you power it on, it outputs a rapid train of current pulses. The total number of pulses it sends in a specific time window is directly proportional to the temperature.
That sounds tricky to read.
It is. To read this accurately, you cannot just pull a pin with software. The CPU is not fast or consistent enough. You have to configure the microcontroller's internal hardware to do the counting for you.
Which means configuring a lot of very specific low-level peripherals. The entire demo is written in about 200 lines of Forth across 6 files. I want to highlight how they achieve this complex timing entirely using readable names. How do they set up the hardware to catch these rapid pulses?
They heavily utilize the hardware comparators and the internal timers. To read the pulses, they configure 2 hardware comparators, COMP1 and COMP2, to detect the tiny voltage spikes from the sensor.
And they use CMSIS names to set the detection threshold to exactly half of the chip's internal voltage reference, right?
Yes. But more importantly, they configure these comparators in an advanced window mode.
Why is window mode necessary here?
Well, in window mode, COMP2 essentially tracks COMP1. Instead of the CPU constantly waking up to check if the voltage spiked, the hardware comparators watch the voltage threshold completely independently. When a valid pulse occurs within the window, the comparator hardware sends a signal directly to a hardware timer.
And that timer, TM2, is configured in external clock mode 1, meaning it isn't ticking based on the system clock. It's only advancing its counter when it receives a physical pulse from the comparators.
They even enabled a hardware debounce filter using readable CMSIS constants to ignore electrical noise.
That is incredibly elegant. This architecture allows the CPU to go to sleep or do other tasks while the hardware handles the high-speed counting.
Exactly. The main application logic just powers on the sensor for exactly 100 milliseconds, waits, and then reads the final tally from the timer hardware. Finally, it takes that raw pulse count and applies the conversion math, dividing by 4096, multiplying by 256, and subtracting 50 to yield the actual temperature in Celsius.
So we have a custom boot file setting the system clock to 48 megahertz via the PLL, intricate pin multiplexing for the LEDs and sensor power, windowed hardware comparators, external hardware timers with noise filtering, and floating point style conversion math.
A very comprehensive demo.
So what does this all mean for the flash memory? What is the final footprint of this entire compiled application on the STM32 chip?
6 kilobytes.
Wait, really? 6.
The entire operational application consumes just 6 kilobytes of flash memory.
That is the ultimate proof of concept. Writing that complex hardware configuration using beautiful, descriptive CMSIS names added exactly 0 bytes to the target chip. The 29 kilobyte readability tax was completely eliminated. The chip only received the dense mathematical truth it needed to execute.
If we connect this to the bigger picture, what's fascinating here is that FURS is entirely chip agnostic at the design level. If you start a new project tomorrow on a completely different Cortex-M microcontroller, you do not have to rewrite the toolchain.
Oh, that's amazing.
Yeah, you simply download the new SVD XML file from the manufacturer, drop it into your project folder, and run make all. The XSLT transforms, the makefile, and the FURS utility words like BSE remain exactly the same. You instantly generate a custom-tailored relational database and substitution rule set for your new hardware.
Your source code continues to read like a beautifully formatted hardware manual while compiling down to raw, highly efficient instructions. And the source notes that the FURS repository even includes embedded freebies, right?
Oh, definitely. Like a full Cortex-M0 disassembler so you can inspect the exact assembly instructions generated in memory, and a custom call trace handler to catch unhandled hardware interrupts.
It provides everything an engineer needs to build reliable, observable embedded systems while entirely removing the friction and cost of hardware abstraction. It is incredibly elegant engineering.
It really solves a massive headache for developers.
Thank you so much for joining us on this deep dive. I want to leave you with a final provocative thought to mull over. FURS solves a critical memory constraint by drawing a hard line between the environment where human-readable abstractions live and the environment where runtime execution happens. The names stay on the host. Only the math goes to the target. Take a look at the rest of the software world around us.
Right. Think about our daily apps.
Look at web browsers that routinely consume gigabytes of RAM just to render text, or bloated desktop applications that take seconds to load simple interfaces. How much processing power, memory, and physical energy are we wasting across the entire tech industry simply because we've lazily bundled our human-friendly abstractions into the very code the machine has to execute at runtime?
It's a huge hidden cost.
What kind of performance could we unlock if we finally learn to leave the labels at home? Think about it. We will see you next time.